Before we start on the new stuff, I've chosen one of the problems for the homework to kind of go through since kind of a lot of people were gone. Figure it's do a homework problem or so to get everybody back in the fold, so to speak. So we're talking about exponential and logistic functions here. So number 10 says the number of grams of carbon-14, denoted as C, present in a substance after T years, I think that's probably supposed to be years, is given by the function C of T equals 20 e to the negative 0.00012116 T. What is the initial amount of carbon-14 present? So C is representing the amount of carbon-14. So we're going to need to plug in a value for T to find that. And T is representing time in years. What does initial mean in time? What number? 0. So we're just going to do C of 0. Now for this problem, I'm going to use my calculator to do this. So there's lots of different ways you can do it, but because there's a series of problems involved in this, I'm going to start by just typing the function into the y equals spot. I got to remember what that was. Negative 0.0021 or 1216. 1216x. Okay. And if I do then vars function y1 of 0, that's just going to be plugging 0 into that equation. I get 20. And I guess this was in grams.
So it's just plugging in basically, kind of like the amount.
Yep. Because T is years or time, we're just plugging this in. If I read part B, it says how much is left after 10,400 years? Well, that's another time, right? So that's going to be plugged in for T. So we'll do this again on my calculator. So I have, like, say, 5.65 grams. Let's round that to 3 sig figs, I guess. Yeah.
In chemistry?
Maybe. This is a chemistry problem. Part C says, when will the amount remaining be 10 grams? So that's a value for C of T. We need to be solving for a T that gives us 10, right? Is everybody okay with my initial setup? So to solve this equation, I'm going to do this graphically. So I have my equation for the amount remaining, and then I have an equation for y equals 10. And I'm just going to look for the intersection between them. So the hardest part here is going to be setting my window to get a decent view. So x is representing times. Well, I know time starts at 0, so that's a good x-min. And I know from the problem, by the time I get to 10,400, I have less than 10 grams left. So that feels like a good upper bound. I'll do like 10,000 as my x max. Is everybody good with how I kind of figured that out by looking at my previous answer? And I guess scaling by 1,000 makes sense. And then the y's, well, the y is the amount of stuff I have. What's the least amount of stuff I can ever have? 0. What's the most amount of stuff I'll have? Is the start, right? How much do I have at the start? 20 and then, I don't know, go by 2s or something there. And then let's hit graph. What a beautiful picture that is. So I'll do second and trace, intersect command, because there's just 2 curves in one intersection. I just press enter 3 times. And I got 5,700 as my value for x, or in this case, really t is what this represents. And then I guess the unit we're using is yees in the problem. This is me leaning into the typo, like that's some kind of measurement of time that I just made up for the problem. It's clearly supposed to be years. Or maybe it is supposed to be yees. I don't know. What do you guys think? Is this okay? I particularly chose this example because we're going to be using these same calculator techniques in 15.2 to do the homework problems in 15.2. So I wanted to make sure that I included that again. Questions on this problem number 10? Okay, you guys ready to dive into 15.2 then? Let's do it. I love the attitude. So in 15.2, we're going to be talking about modeling. So we're going to be like writing an equation to describe a situation, then using that equation to answer questions. So we're going to start with what's called the exponential population model. So the first model we're going to look at is the exponential population model. Now, we call this the exponential population model, and that would make you think that we're always talking about populations of living things. That doesn't necessarily need to be the case. You can use this model for almost anything that's changing exponentially. So the P of t represents the population at some time t. The R is the percent change. T is time, typically measured in years. And P naught, that P with the subscript 0, is the initial population. I spelled that wrong. Initial. That's the population at time 0. Now, worth noting, that the value for R can be positive, which would mean we're talking about exponential growth, or it can be negative, which would mean we're talking about exponential decay. Is everybody okay with that? All right, so let's look at a already written for us exponential population model, and we're going to use that to identify the values for like P naught and R and decide whether we're growth or decay. So our first model is 12,587 times 1.0384 to the T. So if I compare this to my basic formula, I can identify that the P naught, well, that's clearly the 12,587, right? Nobody should have any problem with that. That should be quite easy to see. Now, I can't get the R directly from looking at the formula, right? But I can see that 1 plus R over 100 is equal to 1.0384. Is everybody okay there? If I then subtract 1 from both sides, I get R over 100 is equal to 0.0384. And then I multiply both sides by 100. I get that R is 3.84%. Is everybody so far so good on how I found the R? And because that R is greater than 0, that tells me that this is growth. What do you guys think?
It's a little confusing.
Where did you get stuck at?
I don't know. I'm just trying to understand the process. The first step is finding plugging the numbers into this.
My first step was comparing the equation that I was given to the exponential growth model. That's what I wrote underneath it in red, and figure out which number corresponds with which part.
Okay.
So that's what I highlighted. The yellow parts correspond, the green parts correspond, the blue parts correspond. Okay with that?
Yes.
So that tells me P naught is the 12,000 number, right?
Mm-hmm.
And that 1 plus R over 100 is the 1.0384 number.
And because it's greater than 0, it's showing growth.
Correct. So I solved that equation for R after, and because that value for R was greater than 0, it's telling me this is a growth equation.
Okay.
That the percent change is positive, so it's growing. Oh, great. Yes.
So this is just the first type of problem, right?
Mm-hmm.
What just generally are we going to be asked off of this function model?
Well, you could be asked to do what we're doing right now, would be to figure out the values from the equation. The other situation that we'll look at in a few moments is taking a situation, writing the equation, and then maybe answering questions from your equation that you've written. Okay? Let's do another one of these, though, before we move forward, yeah?
Oh, that was it? Okay.
Yeah.
Okay. Sounds good.
So why don't we take a minute or two, see if you can come up with the values for P naught and R, and decide whether this is growth or decay. I'm going to drink a little bit of delicious soda pop while you work.
I bedazzled an entire Mountain Dew. It looked so cool. Just a fun fact.
How much money do you think you spend on bedazzling?
Okay, well, before I realized they were on
You
TikTok Shop.
bedazzled a mountain.
Yeah. Before I realized they were on TikTok Shop for like $2, I did spend a really disappointing amount of money on them on Amazon. I haven't gotten anything else since then.
Okay.
Dude, I spent $60 buying more.
60?
I spent like $10.
60? No, you can buy a with an PlayStation 5. You can buy El Cinco and maybe like
I'll sing.
maybe like let's talk about PlayStation. Maybe like
It's been like
Dave, where's your PlayStation 5?
a ball
Fresh off Alibaba. Professional TikTok drop.
I don't know what PO is.
TikTok drop.
Like,
All right. Who can tell me the value for P naught? Go ahead, Emma.
P naught is
22,619.
wow.
Wow.
that was not.
Emma, you have a very deep voice.
Oh, what can you go?
Yeah. The R value is
Sorry,
negative
sorry.
1.3%, so it's decay.
Excellent.
Wait, what?
You had it wrong.
No, I just don't understand. Wait, hold on. Hold on. I'm on my way. I'm on my way. I'm like really trying my best here, and that's the best I do. Wait, so how did you get that it was
Didn't really change my grade.
You set the Hannah. You set the two green pieces equal to one another,
Ooh, okay.
and then solve for R.
I have some. It is more transitions.
Do I just like put it in?
I mean, you could type it into you could do the algebra or the arithmetic with your calculator, sure.
And I have this right.
Shut up. Shut up, Mary.
So,
Oh.
what these series of examples
Oh yeah, like the equation. You just plug it in. Okay.
And so that's what I did. Yeah, that's what I did here. This equals this. And then you just do
You just have to
basic
plug in.
minus 1 minus 1.
Did you tell her?
Please. And then times 100.
got it.
I don't.
Okay.
Yes.
So
Neurons are firing.
I was
good.
gonna say the bloodstream is going.
What we've just done,
December, bro.
just what we've just done is we took an equation, we pulled the coefficients off of it, right? What we're going to do next is we're going to take a story and build the equation from it.
Ooh, story problem.
Okay?
Sorry.
Why did you think I was sending?
I didn't.
I want to have more like fun in my life. When can I have more fun in that? If it's a story problem, it's not like a
Okay, I don't.
Yes.
What's your favorite one? Hey, Mary, what's your favorite?
Okay. So this says determine the population model. So I'm going to stop right there because it's asking for a population model. I know that I'm going to be using our model from that I introduced to you guys at the start of the lesson.
Okay, perfect. Just put the model there.
It then says it has an initial value of 15. Well, the initial value is P naught. So I'll fill that in. Increasing at a constant rate of 6%. Oh, so R is 6. And then I can just clean things up here a little bit. Oops. So I'm there. And then I should probably say T is measured in years, right? But that's it.
Okay.
That's the problem.
That's all you had to do.
Is this what we have to learn today? Because that would be amazing.
Wait, I'm sorry.
Yes,
if this
Jacob,
sounds
what's up?
like-
Yep. Hannah, what's up?
I'm sorry if this is really a stupid question. Can you show me how you like just did the math? Because you went from 1 plus 6 over 100 to 1.06.
So I divided 6 by 100 and I got 0.06.
Okay, so I'm dividing 6 by 100.
And then you add one.
And then you add 1.
And then I added 1 to that
And then add 1.
to get 1.06.
And it equals 1.06. Okay.
You know what pound stands for? 705.
I don't know. I feel like every joke you say like an airball.
Oh, wait.
You guys are so.
Okay. Next example. Take a read here. Says determine the population model with an initial value of 15, increasing at a constant rate of 6% every 6 months. What is the only difference here?
You just
6 months versus a year.
Yeah.
So you multiply it by 2, right?
I'm not up yet.
Hang on. Hang on.
You're trying to get for a year.
This is a year, but it says every 6 months.
So we're going to do this, right? Start with our model.
Yes, I got you. I'm up to speed.
What is P naught? 15. What is R? 6. Now, what am I going to do with 6 months?
Put in the T.
So either I can say T, where T is equal to like every 6 months, which kind of stinks because now I have to, whatever my answer for T is, I'm going to have to convert into 6 month like groupings. Or what makes probably more sense is to have T in years. And how many 6 month intervals are in 1 year? 2. So I'll have 2t. And this one is probably easier to deal with, because if I ask you a question about like how many years does it take to get to like 100 people, it's much easier to do that and just have the answer come out to be your answer, rather than if it's the other one, you get your answer, then you have to go, okay, now how do I get years out of this number of 6-month intervals,
Okay.
right? So usually you want to rewrite everything so that the exponent will describe you the number of years. Yes, that's why it's 2t.
Well, I was,
That's okay.
Go ahead, Mary.
I thought like you would just put like exponents, but it's half the year.
Correct.
Whoa.
So that means there's twice as many 6-month intervals in a year.
There's 2 of them.
Mhm.
Yeah.
Stop. Yeah, that's why it's-
There's 20
Got it,
months,
guys, I got it.
dividing 12 by 2. If you divide 12 by, wait, no. So if you divide 12 by 2, you get 6. So then there are 2 6-year months in a year, so then you put 2.
No.
No, we just.
I know, I wasn't here. Wait, that's it? We're done?
I don't think I'm right.
Wait, that was it? That was the whole.
I almost had done that one that nobody would help me on.
Oh, here's
What? I still got a 31, Danny. What did that say about the whole
I
bunch?
should probably check what
On this newest one? Yes, like.
Can I text you for maybe helping me?
No, the last one I got 69, so like, it's fine. Like. And then once I retake that 30%, then more power.
Then you'll have an A for life.
Well, so yeah, I have to retake it and do good on it.
Andy, did you study? Yeah. What grade did you get?
Daniel, you got an 85 and you didn't think to share your wisdom with me?
On this test?
I got a 76.
I got an
Okay,
A.
see, if Rocco did that, then that's not fair.
Yeah, my grade was on 4%.
No, I'm taking something tomorrow.
I just forgot to do the where the X is on the bottom. I forgot.
Oh, yeah, when it's, yeah, I had no
The
idea.
asymptotes and stuff, that's what.
I wrote down random numbers, and then I put a J at the end.
Oh,
All right.
I got an A plus, you got an A.
Let's look at this example. Suppose a colony of 120 bacteria is put into a petri dish, and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. Does it feel clear to everyone that what we're talking about is population here? Because we have a group of things that are growing. So let's use our population model for this. So write down the model that we're going to fill in. What is our value for P naught? 120 is correct. How'd you know that? Because it tells that's how many bacteria are at the start, right? Everybody's clear as to that?
Okay.
And is R?
Okay, now what is R going to be? Nope,
3.
no.
Okay.
I feel like it'd be 400,000. Isn't?
I thought PT was 40,000.
Yeah.
It's E,
PT is 400,000.
yeah, right?
So we're gonna
Just R.
do this in 2 steps. Okay, shh, hold on a second. So that's fair. But I want to do this in 2 steps rather than putting 400,000 into P of T. I'm going to write the model first, and then write the equation that we're going to solve afterward. But it would be fine to condense that into 1 step, but I'm going to do it as 2, so as not to confuse anyone. Okay? So you're right, 400,000 will be P of T. I just want to do 1 step at a time. Okay?
Okay.
Everybody's good still?
Yeah.
What is R though?
We did 2,
It's not 2, but you're on the right. Why did you say 2?
because doubles.
Doubles is the key word here, but doubles doesn't mean 2 in this case. Because remember, R is a percentage.
So it would be,
What percentage would mean double?
no, it'd be 200.
200, right?
100.
100 is double.
Wait, that would be my next.
So if something costs $1 and I increase its price by 100%, its new cost is
$2.
$2. It's doubled.
Yeah.
Does everybody feel okay with that?
Really?
So again, it's one of those where it's like once you've heard it in words, it's like, oh yeah, sure. Of course it's got to be that.
And then T just be 3 hours.
So what unit do you want T in? Well, if you want it in days, it's going to be one thing. If you want it in years, it's going to be something else. If you want it in months, it's going to be something else. If you want it in hours, but we need to pick a unit.
I think they.
Let's go with hours.
I would choose hours as well.
Wait, so why is it different for like doing hours and then it's different for doing months? You know
Well,
what I'm asking?
I feel like it'd be easier just for it to be like a whole number instead of it being like.
So I'd be happy to answer that. Let's finish this in hours and I'll explain to you how it would be different if it's in months.
Okay.
Deal?
Yeah.
Okay. All right.
You have to, every time do you have to put, like, T is, like,
You should get in the habit of doing that because it's really easy to screw this up if you don't. Because just like I was saying to Gianna, depending on the unit of time you pick for T, your equation is going to be different.
okay.
So you want to make sure that you're being careful here. That's why I'm writing down that we're going to do this for T in hours. Okay? So read the problem here. It says that the culture doubles every 3 hours, right? How much of that doubling happens in 1 hour?
Like, a percent.
Like 1/3?
1/3 of it, right? Everybody agree with that? If it takes 3 hours to double, you'll get 1/3 of that doubling in an hour. So I'm going to have T over 3, or 1/3 times T. Everybody okay with that? Now, we could continue, but I'm going to take a little aside here. Okay. If instead we had chosen T to be in days, how many doublings are going to happen in 1 day? 8. How did you get 8, Gabby?
24 hours in a day?
Oh,
There's 24 hours in a day. If it takes 3 hours to double, it'll have doubled 8 times in a day.
Wow.
Okay?
yeah.
So depending on the unit you choose for T, that exponent's going to look a little bit different. It doesn't matter what unit you choose for T. No, it doesn't. Because the problem just asks how long. It doesn't ask for how many hours or how many days or how many months. It just says how long. So you can choose your unit of time to be whatever you'd like. Whatever's convenient to you is fine. You guys okay with that? Or if you wanted to be really kind of like obtuse about it, I mean, you could write it this way. And you could just write it to the T and say that T is just measured in 3-hour intervals. right? And you could keep doing this for whatever unit of time you wanted to use. Does everybody see what we're doing here as to why I want to label the unit that I'm using for t? Because depending on what you're doing, you're going to have your answer will have a different time unit attached to it. And I will care about that come test time, right? If you give me the answer in 3-hour segments and you label it as 3-hour intervals or whatever, great, that's fine. If you say it's hours and you give me 3-hour segments, I'm marking it off, right? Because the unit matters here, because you have the freedom to choose your unit to be whatever you'd like. Does everybody feel okay so far? Daniel. Sure. All right. Let's say for the sake of argument, we're just going to use this equation. Okay? Because there's a second piece to it.
400,000.
The first part of this gave us the information to build the equation. The second part of it then is saying, use your equation to find how long, that's solve for t, would it take for there to be 400,000 bacteria. So we want then P of t equal to 400,000. And we want an answer for t. And because we wrote our equation in hours, we know that our answer would be in hours. Everybody's okay? Okay. So to do this, I'm going to do this on our calculator, just like we've done in the past. Actually, it's probably worth pointing out here. Let's take one more simplification here. Because what's 100 over 100?
1.
And what's 1 plus 1?
2.
Okay, so we'll just say that's 2 to the t over 3. Is everybody okay with that?
Yeah.
Just because it was going to be obnoxious to type in my calculator. It's fine to type in your calculator obnoxiously, though. There's no penalty for that. Is everybody okay with what I entered in Y1 and Y2 onto my calculator? Make sense? Okay. Now for the hard part, which is going to be to choose a window where I'm going to be able to see the intersection of these things. So I'm going to press the window button now on my calculator. Now, X is representing the number of hours, right? So in like 3 hours, I've doubled, so I've gone from 120 to 240. So that's 3 hours. In 6 hours, I've gone from 240 to 480. In 9 hours, I go from 480 to just shy of 1,000. So this is going to be a while to get to 400,000, right? So I don't know what it's going to be. I'm going to just go down and be like, maybe pick 100 here and see how it goes. If I have to extend it, I might have to extend it. Everybody's okay? The minimum amount of bacteria I have is 120. The maximum is 400,000. I'm just going to go from 0 at my min and maybe 500,000 at my max. That should be plenty to see what's going on. And tick mark at 100,000. Is everybody okay with that? Now I could put 120 to 400,000, but I'd like to be able to see above that 400,000 line a little bit also. All right, let's hit graph and take a look. There we go. Wonderful picture. That'll do for me. In fact, 100 was a way big overestimate, but that's okay. I'd rather overestimate and make sure I can see the intersection than underestimate and not be able to see it. So I'll do second trace, intersect command. Because I have only 2 curves in one intersection, I can just press enter 3 times. And there we go. I have 35.1 hours. Is that okay with you guys? Notice if I had done this instead, if I had done this in like 3-hour segments, I do the same thing. So second trace, intersect command, enter, enter, enter. So my answer is 11.7 3-hour segments or 3-hour intervals. And notice that 11.7 times 3 is 35.1 hours still. It's the same answer, just with a different unit attached to it. Okay? On the test or the quiz or whatever, I won't care what unit you give me as long as the answer is correct and labeled, and the unit is labeled. So whether you gave me 11.7 3-hour intervals or 35.1 hours, or if you gave it like 1 point whatever days, it's all fine. But the unit has to be there.
So it was T divided by 3, that was 1 hour?
Correct. And I take the divide by 3 off. Now it's in 3-hour intervals. If it was 8T, it would be in 1 day intervals. So you're just like whatever the unit for T is going to determine what the exponent looks like. Does that feel okay? All right. All right. So there is another special case for the for that population model. Actually, no, that's just fine. Let's just, okay. So let's just do some vocab. All right. How many of you have had a science class where you've talked about radioactive decay?
Like now?
Like ever?
Yeah, it's been
Probably in 7th grade.
Probably in middle school? Okay.
Oh, not to
This
just,
is cross.
I don't remember.
It was like white
Cross,
stuff.
like one of the
so
urban
like
legends.
X-rays and radioactive.
Remember the
Ish.
quarter Chinese grandkids?
Okay. So let's talk about what we mean by radioactive decay. Everybody's all right?
Yes.
So we can conceptualize what's happening here. So let's say you have 100 grams of some radioactive element. What happens with radiation is subatomic particles kind of leak off that element. And as a result, depending on the type of radioactive decay happening, it loses like protons or neutrons or electrons or some of both. And that element starts to turn into a different element, right? The number of protons dictates the element you are. So if it's losing protons, it turns into a different element. But either way, regardless of what it's losing, it also loses mass, right? So at some later time, maybe half of its mass has been lost due to this radioactive decay happening. Okay? That elapsed time is called a half-life. So it's the amount of time it takes for that radioactive substance to lose half of its mass. Is everybody okay with this idea? So very common radioactive decay happens is uranium. I think 235 will decay down into lead. So uranium's what you use in like a nuclear reactor. Actually, probably use enriched plutonium, but like you got to make that first from uranium. or those of you that are like history people, most of the dating done in history is done through carbon dating. So how that works is there's an isotope of carbon. You remember what the word isotope means? It's the same element with a different number of neutrons in it. So there's an isotope of carbon called carbon-14 that occurs in the atmosphere at a known percentage. So like every living organism has certain percent of its carbon as carbon-14 that matches the environment or the atmosphere, because as you're breathing, that carbon-14 is coming in and you're using that to build your cells, and like it stays constant as long as you're alive. Once you're dead, your body stops making new cells, so the amount of carbon-14, the percentage of carbon-14 in your cells is locked at the time of your death. So if we measure what the percentage of carbon-14 is in your dead cell, we can see how long you've been dead for, because we know exactly how long it takes for carbon-14 to decay. Okay? The problem is there's an upper bound to this, because eventually so much carbon-14 has decayed that it's no longer measurable. Right? So there's a time limit that you can't date things that are like millions of years old, because there's just no carbon-14 left. It's all been decayed away. All right. So your takeaway, half-life means that R is going to be negative 50%. Mm-hmm. Mm-hmm. Okay, that's the big takeaway. Let's do an example. Okay. So here it says, suppose the half-life of a certain radioactive substance is 35 days, and you have 10 grams of substance initially. Find the time it would take for there to be only 1 gram remaining. So again, even though we're not talking about living organisms, we can still use this population model. So when I hear the word half-life, I know this means that R is negative 50. And when I hear the word initial, I know that that's P of naught. So I can plug these in. And then what am I going to write for T? What do you want T to be measured in? What unit of time?
Days.
Days sounds great. Okay. So how many how much of a half-life gets completed in 1 day? Nope. Takes 35 days to do 1 half-life. So in 1 day, we get 1/35. So my exponent should be t over 35. Is everybody okay with that? In general, whatever the half-life is can just be the denominator of your exponent. Okay? And now what we want to do is we want to solve for when p of t is equal to 1. Notice that I just wrote x over 35, or 1/2, instead of 1 minus, or 1 plus negative 50 over 100. That simplifies down to 1/2. I just did that quick in my head, just because it was less typing in the calculator. It'd be fine to not do it in your head. Just type in exactly what I had written down is okay too. All right, let's set our window. Again, the hard part is figuring out the x max. If I think about this, after 35 days, I'm going to have 5 grams. After 70 days, I should have 2.5. After 105 days, I'll have 1.25. After 105 days, I'll have less than 1, right? Everybody agree with that? So I'm just going to do my x max to be 100. That should cover it. Now, the most amount of stuff I'm ever going to have is 10 grams because it's decaying. I'm going to be losing stuff. And the least amount of stuff I can ever have is 0. So my y's, go ahead, can go from 0 to 10. Is everybody okay with my reasoning on my window setup? Uh-oh! Maybe I miscounted there.
Wait, what? So what's the issue with doing it like different windows?
Doing it different from the windows.
Like if you made it too big or too small?
Well, here I made the x max too small, right? Do you see them intersecting?
No.
Nope. So let's just go back and make that a little bigger then. So up and down, I'm good. I'm just going to make that 150 or maybe try 200 or something. It doesn't really matter. It just has to be big enough so they cross. So all I really care about is making sure I can see the intersection. But there they do. So I'll do second trace, intersect command, enter, enter, enter. So I have 116.3 days. Or if you had instead written this as, probably many of you will, write it this way, you would need to know that t is in half-lives. So if you did the same thing, and we cut this divides by 35 off, probably can reset the window out to like 10 or something here. And I do second trace, intersect command, enter, enter, enter. So I have 3.32 half-lives. And notice that if I take 3.32 and divide it by, or multiply it by 35, I should get that same 116-ish. So it's talking about the same amount of time in just a different unit. Both answers I would take, provided you have the unit written down next to it. That you wrote 116.3 days or 3.32 half-lives, both I would take, but the unit has to be there.
Wait, I'm just curious. years, do you do it like, you divide it by the 35, do you think it's easier that way? Like, why did you?
I think it's, well, here's the thing, Gianna. I think when you answer somebody, nobody wants an answer in half-lives. They want, like, when someone says, how long is that? They just want to know, like, a unit, like a normal unit of time. But it's not wrong to call it half-lives,
Okay.
right? I'm not going to mark you wrong for that as long as the unit is correct on it and you recognize what you're doing. But I think from a practical standpoint, if I ask you how long something's going to take and you're like, 43 half-lives, I'm like, what the heck's how long's the half-life now? And like, now I got to compute, like, that's an impractical answer to somebody. I'd rather just have like a normal amount of time. Like, if the answer is like 842 months, like that stinks too. What would I rather have there? Years, right? Like you try to give the person the unit that makes the most sense based on the answer. But like from a right and wrong standpoint as a math teacher, I don't care about you giving me a convenient answer. I care about you giving me a correct answer.
Okay.
So if the unit's correct with the number, marking it right. If the unit isn't there next to it and you have the right number, but I don't have a unit, I can't judge whether you've done it correctly or not.
Okay.
Does that make sense?
Yeah.
I was gonna ask if I could use that.
You're welcome. All right. I think that ought to do us for today, guys. Yeah, so you guys should be able to now do up through 36. So we're at 17 to 36 now.
We had 38. We already had to do 1 through 17.
Yeah, I think 1 through 16, but yes.
So what? Like, did I do this Sunday 1 through?
Yes. So this gets tacked onto this Sundays also. So you're up to 36. I just want to point out to you guys that you don't want to get behind here, because if I look at this problem set, there are 184 questions in this problem set. So just like not one you want to defer, like stay on top of this because it like stacks up pretty quick. Now, for the most part, these are not mega time consuming problems. Like once you get the hang of it, you're going to rip these off and like, pretty quickly. But if you got a lot of these stacked up, it becomes pretty overwhelming pretty quick.
Are we gonna have more homework this week?
I'll give you some more on the X day.
16 last week's homework?
Correct. 1 through 16 was assigned on Thursday
Okay.
or Wednesday. I guess we didn't have school on Friday, so it would have been Wednesday.
You didn't have school on Friday?
It was Irish week.
School on Thursday.
We should have a class.
We didn't have school on Thursday or Friday?
No, this
Last
Thursday.
Thursday,
Last week. Oh, no, last week we did. I don't know, whatever. The last class we did 1 through 16. Whatever it was. I'm a week behind, apparently.